Hello everyone and welcome to my presentation. I am Akhil Chandra Gorkala.
Hello everyone, I'm Sairishma Poturi.
We are final semester graduate students at Texas A&M University Commerce, which is now called as East Texas A&M University. Today, I am excited to share my research titled Post-Quantum Lattice-based Cryptography Utilizing Lattices. The goal of this presentation is to delve into the importance of post-quantum cryptography in the age of quantum computing and explore the role of lattices-based cryptography in building resilient cryptographic systems.
As we navigate through this session, I will cover various aspects of lattice-based cryptography, including its foundation, key problems like learning with errors and short integer solution, and its wide range of applications. Now we will dive into the contents of presentation. Here we are going to explore in different aspects like abstract, introduction, literature review, problem analysis and methodology, and next implementation and experiment, results and discussion. We will lastly conclude with future works and acknowledgement of the professor and reference which are we used during this presentation.
Let us begin by seeing our abstract. With the advent of quantum computing, our classical cryptographic systems like RSA and ECC are under significant threat. Quantum computers, through algorithms such as Shor's, can break these systems, necessitating the development of post quantum cryptography. My research focuses on lattice based cryptography as a promising solution. Its foundation lies in the geometric structure of high dimensional lattices, making it resistant to quantum attacks. This study specifically explores two key problems: learning with errors, LWE, and short integer solutions, SIS. These are the backbone of several post quantum cryptographic schemes.
Here we analyze the theoretical underpinnings, applications in public key cryptosystem, and their broader role in ensuring security in a quantum powered world. Beyond this, traditional cryptographic tasks like encryption and digital signatures, lattice based techniques demonstrate remarkable versatility, powering advanced capabilities like secure multi-party computation and homomorphic encryption. And here we also balance between security and computational efficiency.
In essence, our work not only highlights the current state of post quantum cryptography, but also outlines challenges and future research directions to make these systems more secure and efficient in practice. So, next, let's dive to introduction. So, let us start by understanding the basics of cryptography and why it is crucial in the context of quantum computing. So, cryptography comes from a Greek word named crypto, meaning secret, and graphy, meaning writing. So, at its core, cryptography is an art of science of protecting communication. It uses techniques like encryption and digital signatures to ensure not just the secrecy of information, but also its integrity, authenticity, and identity verification. Traditionally, cryptography systems have relied on solving mathematical hard problems like factoring large number or discrete algorithms. These problems are computationally infeasible for classical computers to solve in a reasonable time, which makes them secure. However, quantum computers pose a massive threat to these systems. With quantum algorithms like Shor's algorithm, these problems can be solved exponentially faster, breaking the foundation of traditional crypto systems. The urge has led to development of post-quantum cryptography, a field dedicated to designing algorithms resistant to quantum attacks. So, among these many approaches to PQC, which is post-quantum cryptography, lattice-based cryptography stands out as one of the most promising and well-researched paradigms.
Lattice-based cryptography leverages the geometric structure of high-dimensional lattices. Like coming to this, like in the next slide, like here we have given a figure which is visualize a lattice in 2D or 3D cryptographic applications often deal with higher dimensions. In this figure, we illustrated a simple 2D lattice where you can see how different sets of basis vectors such as black, red, green, and brown vectors can define the same lattice. This flexibility in the representation contributes to the strength and adaptability of lattice-based cryptosystem. The hard problems in these domains such as learning with errors and shortest vector problem and short integer solution are computationally complex, even for the quantum computers. This make a robust foundation for post-quantum security. These problems serve as the basis for cryptographic primitives like digital signatures, message authentication codes, and encryption schemes.
So, the lattice-based cryptography is attractive for its versatility and scalability. However, it is not without challenges. Recent research has focused on optimizing algorithms to minimize computational overhead while maintaining security. At the same time, efforts are underway to standardize lattice based cryptographic methods, ensuring their adoption across various industries and applications. So, in this paper, we aim to explore the foundation concepts of lattice based cryptography and its key algorithms, particularly LWE and SIS, which are learning with errors and short integer solutions. We will also discuss the challenges these systems face in quantum era and highlight their practical applications. Finally, we'll delve into the connections between LW and SIS, ongoing research into their complexity, and future directions for improvement. This research is not just theoretical, it represents a crucial step in securing our data and communication for the quantum future. Next, let us continue with the literature review for research. So this literature review, which provides a strong foundation for our undergoing understanding the role of lattice-based cryptography in a broader field of quantum computing, cryptographic PQC. So foundational concepts in post-quantum cryptography. The concept of this originated from the work of D.J. Bernstein, who highlighted the existent threat quantum computing poses to traditional cryptographic methods such as RSA and ECC. Shor's algorithm demonstrated how quantum systems can effectively solve the fascinating and discrete logarithms problems, essentially breaking these classical systems. This highlighted the need for cryptographic methods resistance to quantum assaults.
Now, coming to the development of lattice-based cryptography, this leverages hard mathematical problems such as learning with errors problem and the shortest vector problem. These problems are believed to be resistant to both classical and quantum attacks. These early contributions include ITEC and Duvok's cryptosystem in 1997 based on the shortest vector problem, though it was later cracked. The NTRU cryptosystem introduced in 1996 became a very notable advancement and is still studied today. A very key aspect of lattice based cryptography is its security based on worst case hardness, setting it apart from other cryptographic approaches. Now, key advancements and applications are the breakage for lattice based cryptography came with the introduction of the learning with error problem by Regev. Ring LWE is developed by Picard, made lattice based encryption more efficient by leveraging algebraic structures. Lattice based reducers or Picard enable secure encryption methods with manageable key sizes, while Dukas enhance digital signatures using bimodal Gaussians.
Okay, so next the cryptanalysis and future directions. However, the cryptanalysis efforts such as Hu and Jia's work on the GGH map revealed vulnerabilities that require continuous assessments and improvements. As the field evolves, initiatives like NIST, post quantum cryptography standardization processes aim to formalize lattice based schemes as cryptographic standards for the quantum era. The ongoing focus is to improve security, reduce computational overhead, and address practical challenges in resources constrained environments. Now, let us move forward with the statement and methodology. So, the main point we are trying to prove in this paper is that lattice based cryptography, particularly through the learning with errors and short integer solution problems, which offers robust and practical foundation for post quantum cryptography systems, ensuring security against quantum attacks while balancing computational efficiency and a real world application feasibility. We visualize the best approach among these two problems in the end during the implementation process. The rapid development of quantum computing has raised significant cryptographic schemes such as elliptic curve cryptography, which is called ECC, and RSA, which dependent on the hardness of certain mathematical problems like factoring large number of computing discrete algorithms, quantum computers utilizing algorithms like Shor's. This is a major security, prompting the need for post-quantum cryptography methods that are resistant to quantum attacks. One promising approach with PQC is lattice-based encryption. Lattice-based cryptographic utilizes the geometric properties of high-dimensional lattices and offers strong resistance against quantum algorithms. This research particularly focuses on two core problems that form the basics of many lattice-based crypto systems: learning with errors and SIS short integer solutions. So now let us go to learning with errors. So LWE has become a fundamental building block for post-quantum cryptography due to its robustness against quantum attacks. This problem in itself involves solving noisy random linear equations to recover a hidden secret vector S. LWE is computationally difficult even for quantum computers, making it an ideal candidate for secure cryptographic systems. The LWE problem comes into two main variants: decision LWE and search LWE. In decision LWE, the challenge is to distinguish between two distributions. One with the data is generated from the noisy linear equations involving the secret vector, and the other one where the data is random. In search LWE, the goal is to actually extract the secret vector S from these noisy linear equations. Here's a brief mathematical formula of the problem. We consider a vector A sampled uniformly from a high dimensional lattice and an error term E sampled according to the specific distribution. The output is a pair A, S plus E, where A, S is the inner product of the vector A and the secret vector S modulus Q. We are talking about this part with the noisy random inner products. So this is a noisy version of the inner product, which makes it difficult for both classical and quantum computers to recover the secret vector S. The noise ensures that even though the system might look a simple set of linear equations, it's computationally hard to solve. Let me walk you through the step. Suppose we have a security parameter n a modulus q generates a random vectors A, and the output noisy linear equations of the form B is A S plus E modulo Q. This decision problem involves distinguish between A, B pairs that follow the noisy pattern, and those are completely random. Decision LW aims to distinguish the pairs AB from uniform distribution, while search LW aims to find the hidden vector S given several noisy linear equations. Importantly, search LWE is computationally equivalent to decision LWE, meaning that if we can solve one, we can solve the other as well. To summarize, the LWE problem is central to ensuring security in lattice-based cryptography systems because of its inherent complexity. The robustness of LWE is what makes it attractive choice for building secure public key systems in the post-quantum era. With this understanding of the problem, let's now move on to explore the methodology behind this based on how we can implement these concepts, build secure systems. Now, let's take a closer look about the applications of LWE, where one of the most impactful application is homomorphic encryption. This allows encrypted data to be processed securely without even revealing the original data, a crucial feature for maintaining privacy in sensitive computations. It enables tasks like multi-party computation and privacy-preserving data analysis, and plays a vital role in fully morphic encryption, which is a key for securing cloud computing. This ability to perform operations on encrypted data while preserving confidentiality is a game changer in privacy focused applications. Another important use case of LWE is verifying quantum computation. Since quantum computers perform calculations using entangled states, it's hard to directly verify their outputs. LWE helps ensure that these computations are accurately even when quantum systems involve complex computing quantum states. Finally, the hardness of LWE, the foundation of cryptographic security, it connects with the challenges lattice like search LWE and decision LWE. The decision LWE problem differentiates between the real LWE samples and random noise, while the search LWE focuses on recovering secret vectors from a noisy data. So these challenges are deeply tied into lattice problems like SIVP and gap SVP. which are critical to maintaining secure cryptographic primitives. In summary, LWE is pivotal in cryptographic research, playing a central role in secure computing, quantum verification, and foundation of modern cryptography.
Now let's dive into short integer solution, which is another critical component of lattice-based crypto system. The SIS problem is closely related to the shortest vector problem, which is the goal is to find a short vector within a lattice that satisfies specific linear constraints. In this case of SIS, we are tasked with finding a non-trivial vector that satisfies the equation Az equals to 0, which we can see in this one, where A is a matrix and Z is the sort vector. Just like LWE, SIS is believed to be resistant to quantum attacks, making it a promising candidate for post quantum cryptography. It also serves as a foundation for constructing various cryptographic primitives, including digital signatures, hash based functions, and even fully homomorphic encryption. In simple terms, SIS involves identifying a short non zero vector in a lattice defined by a matrix A. The goal is to find a vector set that satisfies the equation Az equals to 0 mod q. Here, q is a large integer often chosen by the proportionate size of the lattice. Let me walk you through the formal definition. Given a matrix A which is composed of m vectors in ZQN, our task is to find a small non-trivial vector z such that linear combination of the vectors result is 0 modulo q. This means we are essentially looking for a vector that lies in the null space of the matrix A modulo Q. One practical application of SIS, that is short integer solution, is in one-way hash function, where it's computationally difficult can help in securing these functions. Additionally, SIS plays a vital role in key exchange protocol, which allows secure communication between parties without directly sharing keys, and it forms the backbone of many post-quantum cryptographic schemes. So, to summarize, the SIS problem is about finding a short non-trivial vector in lattice, and while this problem is computationally hard, it serves as building block for secure cryptographic protocols that are resistant to quantum computing attacks. Now, SIS, let's take a look at its applications. Parity check. Let's take a very deep look into the parity check matrix and its role in lattice based cryptography, particularly in the context of short integer solution. At the core of this parity check matrix A, which is a matrix defined over the integers modulo q, this matrix has n rows and m columns. The key idea here is that A plays a crucial role in defining a specific kind of lattice. The Q array integer lattice denotes LA. In simple terms, the lattice consists of all integer vectors z such that multiplied by matrix A, the result is the 0 vector. Mathematically, it is represented as Az equals to 0 mod q. This means the vectors that forms this lattice are orthogonally to all the rows of the matrix A. To help visualize this, let's take a look from figure 4. It shows two lattices in two-dimensional space. The lattice points are represented as red dots, and these points represent integer combination of the basis vector scaled by modulo q. The lattice on the left is formed by the parity check matrix with q equals to 0, while the lattice on the right is equals to q equals to 4. You can see that the spacing between the points charges between the modulus q. The smaller q results in a denser lattice, while a larger q defines to be a sparser lattice.
Okay. So next we are moving to our next slide, which is SIS, the short integer solutions versus learning with errors, LWE. So we often encounter problems that appear simple but are incredibly difficult to solve. To such problems are short integer solutions and learning with errors. While they might seem similar at first glance, they have distinct characteristics and applications. So the problem statement coming here is, let us start with SIS problem. Imagine a system of linear equations where coefficients and the solution vectors are all integers. The matrix A influences the lattice structure by imposing specific constraints on the integer vectors. These constraints restrict the vectors to points in space that satisfy Az equals to 0 mod q. The value of Q directly impacts the lattice density and arrangement. A smaller Q creates a denser lattice with points close together, while a larger Q results in more spread out lattice. So now why is this important for cryptography? So the value of Q is crucial in determining both the security and efficiency of lattice-based cryptosystems, like learning with errors and SIs. A well-chosen ensures a good balance between the hardness of the lattice problem, making it hard for an attacker to find short vectors, and practical concerns like key size and computational efficiency. To summarize, the parity check matrix that is associated with the lattice plays a private good role to this. Now the goal is to find a non-zero solution vector that is as short as possible. This problem computationally challenging, especially the number of equations and variables is large. LW on the other hand is a decisional problem where a matrix A and a vector B. The question is whether B was generated by multiplying a short secret vector S and A and a small error vector E, or if it was chosen uniformly at random. This problem becomes harder as the error vector becomes smaller. So now coming to the problem type where SIS is computational problem, meaning we need to find a specific solution, whereas LWE, however, is a decisional problem and we need to distinguish between two distributions. Then we have solution. For SIS, we may have a valid solutions with each different length. The challenge lies in finding the shortest one. In contrast, LWE typically has a unique solution if the error vector is small enough. So the relationship, interestingly, LWE at least as hard as SIS. And this means that if we can solve SIS efficiently, we can also solve LWE efficiently. However, the reverse relationship is still unknown. We don't know it at the moment of time. So coming to applications, both the SIS and LWE have found numerous applications in cryptography. SIS is used to construct one-way functions, collision-resistant hash functions, signatures, and identity-based schemes. LWE, on the other hand, is a fundamental building block for public key encryption, oblivious transfer identity based encryption, and fully homomorphic encryption, allowing for powerful cryptographic operations on encrypted data. So, in conclusion, I would say SIS and LWE are two fundamental problems in cryptography, each with its own unique properties and applications.
Next comes our implementation and experiment part of our research. The goal was to assess the computational effectiveness of two post-quantum cryptography methods, that is short integer solution and learning with errors. In this experiment, we implemented both SIS signature system and a basis LWE encryption scheme. Our primary focus is to assess how these techniques perform at various key sizes, and we measured the execution time of these two operations to gauge their computational efficiency. The implementation was done using Google Colab, a cloud based platform that provided an ideal environment for computation and visualization. We utilized several Python libraries like NumPy, SciPy, and SAGMath. The SAGMath was particularly used for handling the lattice related computations as it supports high precision operations which are critical for cryptographic processes. To measure performance, we used the Python time packager to record the execution time of cryptographic operations, like for each key size like 128, 256, and 512. We calculated the execution time by noting the start and the end time and then averaged the results to minimize the impact of these two random variations. The result was visualized using matplotlib library. The performance comparison graph displayed the execution times of SIS and LWE. The x-array axis represented the different key sizes while the y-axis showed the execution time in seconds. We used square markers for SIS and circular markers for LWE, while allowed us to visually compare these two methods for performance at different scales. Results and discussion. The code snippet uh, Yeah, here in this one, the code snippet illustrates how lattice matrices are generated and utilized during the key generation and encryption phases of LWE and SIS. A randomly generated lattice matrix A as a public key for both LWE and SIS schemes.
Okay. So now let me show you the code for which we used Google Colab and generated good output for our problems. So now, so this line initially, which installs the Python packages as NumPy, Script, MATLAB, SageMath for numerical computations. And so I'm just running this line, and it says already satisfied because I already done it a number of times. And then we have the second line which says import numpy as np from script login import solve. So this is basically we are importing some numpy libraries and other all libraries to do some mathematical computations. Okay, it was also done. And then now it's all the same. It says SageMath. We are importing SageMath too. And then we have this this is to generate a random matrix A of size dim comma dim with values between 0 and q for the public key, and where s equals to np, this thing generates a random noise vector e of length dim with values of -2 and 2 for encryption noise. And the next line says that the computation of ciphertext b by performing matrix multiplication and of a and s, and then adding the noise vector e, and turn ab return after for just a public key a, ciphertext b, and a secret key. I'm just running it once again. And then we defined another function which says the sysgenerate, where it generates a random vector z of equal size of number and columns in A with values between n and n. So and the next line for z, we are just checking. Okay, for the z, we are just checking if a dot z equal to 0 mod q. If not, we are regenerating z until the condition holds. So, and the while loop here regenerates z if the condition a dot z equals 0 mod q is not satisfied. It just regenerates itself in the while loop. I'm just running it, and then okay, so here I have another importing the time, where the start time and end time. This is important for our graphical representation, the start time and end time. Okay, then I have the pip install matplotlib. So I'm also including the matplotlib library for plotting graphs. I don't know why I have some latency. Maybe it's because of Zoom. Okay, now I'm importing time to measure the execution time for the code blocks. And then I'm doing the function to simulate SIS signature generation. This replaces with our SIS implementation. Okay, so yeah, and so finally, I'm importing a matplotlib library. So here we have the key sizes 256, 512, and 1024. Previously in my presentation, I mentioned uh, some yeah, in I have a graph for the below graph is for 128, 512, and 256. But now I'm doing something different. 256, 512, and 10. This is the graph for 256, 512, and so as we can see from the figure, the both LWE and SIS are okay. As we can see from the figure, the both LWE and SIS execution times rise with the key sizes as predicted. The rates of growth, however, vary greatly with minimal variations in executing time. Both methods exhibit compatible performance by reducing key size. For example, LWE and SIS both have execution speed of 0.02 seconds at 128 dimensions, indicating a low computational overhead. The further discussions of this experiment, which have applications in the choice of post-quantum cryptography methods, for instance, in situation like real-time communications or embedded systems, with constrained processing capacity, where computational efficiency is crucial. LWE-based techniques might be chosen because digital signatures and data integrity verification are two examples of the applications that may benefit from SIS-based systems, even though they have a greater computational cost.
By this, we conclude that the performance and the computational effectiveness of cryptographic systems based on the short integer solution and learning with errors. mm, Sorry. Based on the short integer solution and the learning with errors problem are thoroughly examined in this work. According to experimental assets, the SIS provides stronger security guarantees, making it the best option for applications requiring more security, even though LW is more computationally efficient and appropriate for performance critical cases. According to the theoretical predictions, the graphical analysis shows scalability issues as key sizes grow. The study helped choose us and optimize cryptographic primitives for safe future systems by highlighting the advantages and disadvantages of both LWN and SIS. It also provides important insights for the feasibility of post quantum cryptography.
Coming to the future works, while the current study provides valuable insights into lattice-based cryptography, there are still many avenues for the further research. Firstly, we would expand the security analysis of LW and SIs by investigating their resilience to quantum attacks under different noise levels and key sizes. Additionally, there is a need to optimize implementation, leveraging hardware acceleration such as FPGAs or GPUs could significantly boost performance. So finally, evaluating the cross-platform performance across distributed system, cloud environments, and edge devices would offer more deep insights in how to adapt these protocols for diverse settings. These future directions are critical for improving practical and scalability of post-quantum cryptography in the real-world applications. So these are the references which we have used in our paper. Finally, acknowledgement.
Thank you so much, Professor, for giving us this opportunity to work
Thank
under
you.
your guidance.
Thank you, Professor. We would like to extend a heartfelt gratitude to Dr. Sangsu, Regents Professor, Computer Science and Information Systems, for his invaluable guidance, mentorship, and support throughout the course of this research. His insightful feedback and encouragement have been instrumental in shaping the direction and scope of this paper. We are also thankful for Texas A&M University Commerce, which is also called East Texas A&M University, for providing a conducive academic environment and accessing to the necessary resources that facilitated our work. Additionally, we acknowledge the contributions of our colleagues and peers who constructively discussed and feedback have greatly enriched the quality of our research. We are also grateful for our family and friends for their unwavering encouragement and support, which have been a constant source of motivation. Finally, we wish to express our appreciation for the broader research community for their pioneering work in post-quantum cryptography, which served as foundation of our exploring of quantum attacks on lattice-based cryptosystems. So it's the end. If you have any other questions, you can also email me, and I'm also available in multiple platforms like LinkedIn, ResearchGate, and GitHub. Thank you.
Thank you.